Hello everybody, I've got this CTEK MXS10 sent in by a YouTuber. Actually, I got inundated with CTEK repair requests. And so I succumbed to the first one because I hadn't seen inside one of these. And if you look at the previous video that we did, I asked everyone if they could tell me what these chips were. I'll just take the lid off. I've had this apart. And you can see in the previous video that, let's get some tweezers, that they scraped the ident off the chips. That was the main problem, and so I shout out to everyone, can you tell me what these chips are, because at the factory they have removed the idents on all the chips. Actually on the PWM one on the back, on that one as well, has been scratched off. This one's okay, that one's okay, but yeah, so they're obviously a bit paranoid about someone copying this wonderful design, although I wouldn't use it if you paid me. Sorry, my big, very large loudspeaker's just fallen over. Right, okay. So where are we at? We've got the chips because someone kindly, literally the next day, came back with these, and they opened theirs up, and theirs didn't have the problem with the chips. Their chips had the idents on, but they had a problem with this. These devices burnt out here. This and this burnt out. They said they charged a car with the ignition on, or something was loaded, the relay that operates the glow plugs that got stuck, and this thing was just pumping the current directly into the car, you know, all the time, running at 10 amps all the time, and these got burnt out. And these are just FETs, which are isolation FET packs, you know, field effects high current transistor packs, which basically switch the battery connections in and out. This is the battery wire here, this one. So they're burnt out, and if you look on the back of the board, they've actually got room for two more in parallel. They're in parallel, these devices, and you can actually put four on. So the designer thought they needed four, but the management probably said, "No, we'll just put two on. That's all right with you." But that would burnt out, and we had another burnt out component. What was it? I can't remember. But there's a fuse here as well, I think. Is that plug on? That's soldered in. That's a fuse, I believe. Yeah, look, you can see they've soldered in a car fuse, and it's a 30 amp car fuse there, so that's to protect the electronics. So I'm guessing when you reverse connect the battery, so you've got the terminals mixed up with the battery clamps, so you're putting reverse polarity. I imagine this circuit would isolate. You wouldn't need to rely on the fuse, so the fuse must be a last ditch attempt if electronics in here go short. 30 amps, quite a lot of power. It'll be a big smoke bomb, if not a fire hazard. I'm presuming it's CE approved in UL, and that the UL standard and the CE standard requires you really to use V0. There you go. So this is a self-extinguishing PCB. So if you put a blow lamp to this, as soon as you remove the ignition source, the flame should go out. You get like flaming while the heat and the gas is being driven off. But it's got some kind of chemical which gases and extinguishes the flame, so it shouldn't catch fire. It shouldn't be self-igniting, or shouldn't be able to sustain its own combustion, but it will burn in a fire. All right. So anyway, 30 amp fuse down there. I'm pretty surprised about these pots. For a piece of equipment that's expected to be used in a damp environment, you'd think they're not the ideal thing. I'm guessing they're setting for 3 currents for 3 stages, perhaps. Odd choice. You'd think you'd calibrate that in software, to be honest. That's what I would do. And then you've got a massive common mode rejection choke. And look, it's supposed to be fixed down, but it isn't. It's broken free. Do you think it's been dropped? I think this may have been dropped at some point, and that's broken off. It's just not anchored down well enough. But it's a big choke. That's the part that I said that should be. Even the Noco Genius 10 has got a tiny choke in comparison to this. This is the big sort of filtration choke to stop the conducted noise from the switching power supply being broadcast out of the wires and blanking out equipment and giving EMC interference, as we discussed before. Big bank of smoothing capacitors on the secondary side. The transformer, they haven't anchored it down. Usually when you drop a piece of portable equipment like this, the transformer, because of the inertia and the mass of the transformer, it will carry on going, and it can put a serious strain on the leads. And quite often you open up a piece of kit and it's been dropped and the transformer has wrenched itself out the board because the housing stopped suddenly, but the transformer kept going and pulled its legs off. And quite often on the fine primary windings you get the pins pulled out and the primary wire has been pulled off the pin, so the primary is open circuit. So if you see an open circuit primary, take the transformer out. You can often repair them just by, you know, doing a bit of close-up surgery on the wire and reattaching it to a new pin and maybe putting a little extension piece in. I've done that many times on power supplies, especially with custom transformers. But I've just noticed something here. Look at this. This is the rectifier on the secondary side, but look at that screw jammed into the... I can't get my tweezer tip down there. That is jammed up against the winding on the transformer. So that's a mistake. That's a factory error that's been overlooked. I'm going to have to take that screw out and put a shorter screw in. Bad design. I can't even move it. Is it pushing it over? Probably is. Look, you can see that in there, can't you? You can see that pushing against there. Bad design. And then likewise on this side, these ones aren't quite as bad because the transformer is convex in that direction. You've got the bulge of the winding sticking out, and it's fattest in the middle. But yeah, there's a little bit of space and freedom on there, but not on that one. So that screw will have to be dealt with if we ever get this working. So you've got a standard type of arrangement. I did go through this briefly before. We've got our mains input fuse. We've got the varistor, 275 volt AC working varistor. This is not a universal product. It only works on 220, 240 volts AC. You've got the inrush limiting negative temperature coefficient resistor there. So that is something like 20 ohms when you put the power on. So these are shortage, and the power goes from the main straight through to your bridge rectifier. You're going to limit the inrush current to 10 amps. Whereas if you didn't have that in, it could be anything like 50, 60, 100 amps. It's really quite a rush, and it's not good for your capacitors to be charged up with such a high pulse of current. You know, suddenly they're sitting there uncharged, flat, or discharged, should I say. Power comes in and go, oh Christ, what's going on here? Don't like that much, and it'll reduce the life of your caps. That's one problem. So anyway, huge filtering capacitor. Look at the size of that thing. I mean, that's a 0.47 microfarad X2 class 275 volt AC working, so multiply that by root 2 to get the square root of 2 to get the DC, what, 430, 415 volts, something like that, 400 volt. Bit of silicon on there. And another big one, so that's 0.47, that must be, yeah, it's a 1, look. They're not cheap, them caps, you know. On the Western market, you'd be paying £1 each for one of those. And a big filter. So clearly filtering the noise from this thing has been an issue, and part of the issue is you've got a plastic housing, which is not going to help, frankly, and you haven't got a multi-layer board. It's just a 2-layer board, which again won't help. Normally if you put the ground plane or the power planes inside the board, inside an internal layer, you can, you know, mitigate a lot of the EMC issues, especially the radiated EMC, which comes out as a transmission rather than the conducted EMC, which is radiated by the power cables. Conducted, i.e. it's taken away and radiated outside of the unit by the interconnecting wires or housing. So there we have it. And yeah, so we've got the filters, the bridge rectifier, another choke, 2 reservoir caps, and down here, look, you've got 2 transistors. Are they the same? Yeah, SR250P. So probably stop transistors, a pair of them, both the same. So if they're arranged in a bridge, one of them will be the low side with the source connected to the AC 0 volts by a current sensing resistor, and this one will be wanging up and down. So the source of this one, because it's not a P channel, it's an N channel, the source will be moving up and down between the supply rails if it's switching the input to this transistor, which means that we need something, because the gate voltage has got to be referenced to the source, and the relationship between the gate voltage and the source voltage has got to be maintained. Otherwise it'll just blow the FET up. So this is probably a drive transformer. There's no circuitry, there's no schematic for this, but this is probably a bifold wound drive transformer to condition and drive the drive signals into this FET. We'll check that out later. Could be wrong, but and if this, the center point of this will be, because this is probably a resonant design, it's quite a small transformer for a 10 amp. If you look in the Lidl battery charger, transformers are almost as big as that, and it's only a 5 amp device. This is 10 amps, so this has got to be by necessity more efficient, otherwise this thing would get too hot without a fan in a sealed box. So we're quasi-resonant, and all the power for the connected to the primary of the transformer is driven through this capacitor. So it's an AC waveform driving the capacitor. There is no DC connection in terms of resistors or inductors or any other wires to the center point of these two FETs, which is switching up and down, just this capacitor. And it's quasi-resonant, meaning it attempts to make the switching points of these during a point in the waveform, either on overshoot or drive, where the current is 0. So if you turn the FETs on and off when the current is 0, then there's no switching losses, because the on resistance of the channel in these things might be 0.1, 0.2 ohms. So only during switching that you get the losses, and that's where the losses come in on a normal flyback, where you're switching all the time, pretty much the full supply voltage. And then during that slope, when the transistor is not on or not off, it happens very fast, but that's when the power is dissipated in it, not when it's switched fully on, because the resistance is so low on channel resistance. So we've got flyback diode, another diode there, I don't know what that's for, another supply diode for this. This is another PWM chip. This circuitry here is looks like it's controlled by this NCP on semi chip. It is scratched off, but that kind YouTuber told me what it was. And you've got here, you've got the low side FET, high side FET. There's the current sense resistor. There's some conditioning circuitry for driving the FETs, and this is an NCP chip. I'll show you the data sheet. So this is one power supply. Okay, there's one power supply. That's the bulk power supply to supply your battery charging current at 10 amps, going that way. This side is high voltage, that is low voltage. All right, so yeah, we've got all the normal things. It doesn't look like a very nicely laid out board, really. Does it say what that is? Right, so the plus leg of the bridge rectifier is that one, and the negative leg is that one. So that must be B minus. The 0 volts, is that? Yeah, it is. Look, there's the band on these capacitors. There's one capacitor there going directly to the output of the rectifier. The positive voltage rail goes through this coil to there, to the other capacitor. So you've got one capacitor connected directly to the rectifier, goes through a filtration coil to stop EMC or RF noise coming back out, and then there's a second capacitor filtering. Looks messy, doesn't it? This board was covered in a horrible, you can see where I've brushed it, can you see that? But it was covered in this white layer of flux residue, which I'm not comfortable with, but I haven't looked at the data sheets. Maybe it's not affected by moisture these days. The danger is when you've got some ionic resin or residue on the board and some moisture comes and condenses on it, it becomes conductive, and then you've got issues with the board. Now, yeah, so we've got two supplies. Here's the half bridge supply for the bulk of the power, and then this chip, as I know, looked on the data sheet, is another separate power supply. So there's two power supplies on here, running a integrated CoolMOS chip, probably a GaN-FET device, Infineon, this one. I'll show you the data sheet on that in a moment. And yeah, noise filtration capacitor, bootstrap supply capacitor. I'm not sure why there's two there. We'll look into that possibly. Then the small transformer associated with this one, these two, that one switches through there. A couple of reservoir capacitors, 7805, 78L05, low power 5 volt regulator. So there's obviously, this is providing the steady, stable electronics supply voltage for the electronics and the measurement. It's and the other thing is, of course, that this, it being CE approved, will necessarily have to have a very low power supply current drain, i.e. in standby, it has to be very low. And if the power's on, then this is a very low power device. It's got burst mode switching, and it's just supplying a few milliamps to the electronics on the other side, and very low power. And I expect that this one is fully shut down when the battery charger is turned off. I'm not sure, but that's the way I would do it. But it's a lot of extra cost, and the problem is that if you've got this power supply here pumping 10 amps through, or as little as 100 milliamps, when by the time you start to do the float charge or the bulk charge or the absorption charge, what you want to call it, the current drops down to 170 milliamps. You only have to drive this very tiny amount, because you're driving out, is that 1%? 100 milliamps to an amp? Well, yeah, 1% of the actual maximum output power is just trickling a bit of power through here to get the required low current for the completion of the I think they call it the float charge, I call it the absorption charge of the battery. So there you have it. That's the circuit. And if I just turn her over, we looked at this before, not much to see really, lots of tracks winging all over the place. Quite surprising to see this thin track here. Look, can you see that? Quite surprised to see that. That's obviously, I hope it's not the power tracks to this device, but it's probably, because it goes out in the region of the FETs, the power trench top power transistors, or whatever they are. That's going to be the FET drive signal, I should think. So why is it not working? We don't know. Interestingly enough, or quite interestingly enough, is that I saw a few of these people have said, oh, I had one of these and I bought it, and after 9 months it blew up. I had it connected to my car, I went out and it was just dead. Been on there supporting the battery, out under the bonnet of the car or in the garage, came out and it had just died. And they said, oh, phoned up CTEK. They said, okay, send us a picture of your battery charger. Just cut the leads off and throw it in landfill. And this one's had the leads cut off, but someone's obviously reinstated the leads, because I'm wondering if this could be a battery charger that's been replaced under warranty, i.e. this is the failed unit and the owner's got a new one. I don't really care really, because as long as they don't go into landfill, I don't mind. That's the thermistor, by the way. Can you see a little titty inside there? That's the actual thermistor for temperature compensation. So this one does claim to have temperature compensation on it. Yeah, so anyway, this could be a warranty replacement unit that we're going to fix, which is doubly satisfying. If they designed them right in the first place, they wouldn't have to fix them, would they? Especially with screws jammed into the windings of the transformers. Honestly, really? I don't know. These production engineers, the trouble with the engineers that design these things sit in their ivory towers, and then the poor guys on the production line just have to make the numbers, and they're quite lazy, to be honest. If the production engineers would be any good, they'd be design engineers, wouldn't they? Yes, they would, but it was just too difficult for them. Anyway, so that's that. Why is it not working? So let's just do some metering on this and just check to see if there's nothing obvious before we put power on it. Good idea. So there you can see the meter up in the top corner of there. Get me probes. Disconnect the mains. Okay, so you can hear the beep presumably as well. That should be enough for most of you to keep you satisfied. So let's just check the diodes to start with. We can see various diodes down in here. Let's make sure, let's check that one. Open circuit that way. Yeah, so that diode's not shorted anyway. There's another one here, look. There's another one, just this one here. Open circuit, effectively 0.6, so that diode's okay. It's just that you can bugger about for ages, and then you think, oh shit, I wish I had to check the diodes first, because it's an unusual fault, and they're worth just double checking. Generally, when they are failed, it will be pretty obvious. Here's the snubber diode, open circuit that way. That's a fast silicon diode, 1/2 volt, which is pretty good. So those diodes are all okay. Let's just check the FET, see if there's any shorts on the FETs. No. No, there's a protection diode in the FET there. No, so that one's okay. And so is that one. That FET's okay. Right, short across the capacitors. As I say, this is the negative here. We just, now you can see that climbing, and that's, make sure that's connected. Yeah. Is the mains fuse blown? The mains fuse down there in the corner. Just check a quick whiz round. Quick whiz round with your meter for your power up, and you might even find the fault before you start. Right, so there's no shorts on this as far as we can see. We could also check the rear reservoir capacitors on the other side here, so I presume that's negative. You can see them charging up. So there's no absolutely dead short on that. Yeah, so that's okay. Nothing particularly obvious, I should think. Solder joints. Should we have a look at the solder joints to see if the solder joints are all okay? Yes, why not? So we're looking at the power supply side again. That's a bit suspect there, doesn't it? That 100 ohm resistor in the middle looks a bit iffy, and the 8R2 does as well, doesn't it? Is that 8.2 ohms, do you think? I'm going to check those in a moment. That 100 ohm resistor doesn't seem to match the rest, does it? It's a different style, doesn't mean much really. Well, I can't see anything particularly iffy, can you? Let's just check those resistors before we power up. So we're on resistance mode. There we are. Are we on ohms? Yeah. Yes, we are. So that's 10 ohm. Yep. Is that 8.2 ohm? 4.5. Okay, so that's, those two must be in parallel, are they? I don't know, actually. Maybe I misread that number. Okay, so there's one component. You can see that dot there is the epoxy used to glue on, so there's normally a component possibly on there that's not fitted. So that's never been populated. It may supposed to be there and was never, it flew off the machine before the placement put it down. And yeah, I wonder if that's, I mean, usually when you're not fitting a component, you don't do the epoxy blob because it's a waste of time. Imagine if you had a load of options populated and you're sticking the epoxy blobs to stick the component down during wave solder. This goes through a wave to be soldered. You'd think, well, so if you see a blob, either the production engineer hasn't programmed the machine properly or the component's fallen off and it's been shipped without it. I wonder what that does. I wonder what that connects to what. Clearly it must have worked when it left the factory, this thing. Anyway, let's put some power on it and see what we got, shall we? Let's not procrastinate any further. Lovely sunny day in the UK today. Spring has arrived. Right, connect the mains in the connector block. Now we've got, I'm just going to put it on 150 volts at the moment, or thereabouts, rather than the full Monty. And as usual, the live wire here on my bench over there is a big, one of those big sort of ornamental 100 watt filament light bulbs, and this is connected to the mains via a light bulb. So if anything catastrophic shorts on here, it doesn't go bang and fly off and hit me in the eye. The light bulb comes on. So a lot less dramatic if you power things. And also this is isolated, so if you do work on one of these, then make sure you know what you're doing, because I can't take responsibility or refuse. And if you're wondering about how many people get killed by UK mains every year, electrocuted at 240 volts, have a look at the death certificates. You'll be surprised how many there are. I've had loads of electric shock, so by extension I'm kind of lucky to be alive, I think. Right, okay, so power on. Power meter on, so I can see how much power's going into this thing. Turn on the old Yokogawa. Yeah, so now power is on. Light bulb is not on, just glowing very, very gently. That's probably just the power charging the caps. So what have we got on the capacitors? You can see the voltage there, yes you can. 186 volts on that one. That's quite nice, isn't it? Yeah, that's about right. Root 2 times what's going in. So, and it goes through this coil to the other one. And there we have it. Alright, so we've got power. I wonder if there's any power getting onto the actual FETs. No, 1/10 of a volt. So that one's got power on it. That's the power rail going in from here. That's the high side switching FET. Don't short anything out. Nothing going on in the other one. So there's no switching going on as such. Ah, dear. So let's just have a quick look at the data sheet, shall we? Which one should we pick on first? Let's pick on the Infineon chip. So here it is. It's a Infineon cool. There's the part numbers. There's the part numbers going down. Well, what have we got on this chip? So what we've got cool set 50 volts, cool MOS, probably a gang FET, very low heat, very high efficiency these things for a single-ended power supply, and startup cell frequency jitter mode. The frequency jittering is for low EMI. If you've got a power supply running at 75 kilohertz, and then the harmonics of that, well, if it's running just at 75, the harmonics for that fundamental frequency will just be concentrated in peaks along the spectrum. And the EMC spec states that, you know, basically any particular the radiated energy, any frequency shouldn't be above a certain level. Well, if you jitter the actual fundamental, if you think about it, you're jittering the frequency, you're varying the frequency quite fast. It's almost like spread spectrum, but not quite. But it will spread that energy instead of appearing in single peaks in the harmonics up into the range where you have to test for harmonics for EMC specification. It'll spread those out, so they're not concentrating on peaks. They're dotted all over the other place, So when you do a peak hold or an average interference, it's spread out, so the whole spectrum rises very slightly rather than having distinct peaks, which will cause you to fail the EMC test. And you can see this one's 67 kilohertz, so that's enough about the chip. It's an 8-pin package. There you can see it. Regulation transformer, snubber, bootstrap supply, diode rectifier. So where does this get its startup supply from? Well, the answer is when you turn the power on, the thing's not running. Power comes down here, the DC goes through the primary of the transformer down to the drain connection, and there's a startup current limit startup to switches on momentarily, and then to provide power in there. Clearly, because this has got quite a lot of voltage on it, it can only really charge this capacitor up once probably, and then the bootstrap supply will take over from the transformer, self supply, and this will shut down because you've got 300 volts coming in here. This is going to get hot pretty quickly, and so it is a vulnerable component. And usually when these things don't run for whatever reason, this startup cell is very often blown up inside the chip for whatever reason. And I've seen new chips out of the box, you put them on, they run for half an hour, and then they go and then you put another chip on out the box, and they survive. So this is a weakness inside the device, and it really only needs to be used once or twice. But turning on and off, on the power coming and off, you know, intermittent power supply, bad mains connection, causes this to fail, and you don't get your startup supply. But often when you put the voltage on here just by a power supply, isolated obviously, the thing will spring into life. So it's clearly this device that's going to have 200 or 300 volts across it. The small current is going to get quite hot quite quickly, and is vulnerable. It's a high voltage switching device, and they fail. So that's that chip. All right, so now if we scoot down on here to have a look at the pins somewhere, you can read the old data sheet if you want some bedtime reading. So pins and pins number, so there's the pin numbers there. That's what we want. That's what we want right there, is the pin numbers. Okay, so let's go back to the unit and do some measurements, shall we, and see what we've got. Alrighty ho, so where are we? Where are we? Where's my other lead gone? That's the question. Alright, so now looking on this cool set chip, it's on don't touch it, so pin 1 is that end, so 1, 2, 3, 4, so it's the 2 pins on this end, okay? 2 pins on this end. They're connected together by a track, look. Oh no, they're not connected by a track. They come down there and there's a 0 ohm link between the two. See what we've got on there then. Nothing. 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 We are still turned on, aren't we? Yes, we are. So where's the bloody B plus gone? Normally I'd be looking for a diode or a resistor. If there was a short in that device, we'd be getting some serious heat being generated, and I don't think we are at the moment. Let's have a quick look with the old camera. Well, nothing particularly. There's just one little dot of heat. Can you see that? It's that resistor there in that chain. That chain of resistors there is just, you've got like 1.5 microfarads across the mains, haven't you, of those filter capacitors. Quite a lot of reactive load. And if you pull the plug out at peak cycle, those caps will be charged to 250, and that will give you quite a tingle. So that all that chain of resistors is there is just to discharge those big input filter capacitors connected to the mains. But there's no other source of heat on here, and there's nothing else getting hot that I can see. So no, so we've got somewhere where the power supply is disappearing. The B plus is not. The B plus is gone. AWOL. B plus has left the building. All right, ho. So what's happened? I think we're going to have to debug this board, aren't we? Yes, we are. Right, let's do that. So let's turn the power off. Let's get the shorting resistor. Seen this before. It's a 10 ohm resistor to discharge these big reservoir capacitors. Well, not that big. Well, there's some power there, so they're holding their charge. All right. Okay. Let's get up close and personal. Show me what you got. There we go. So looking at this, we've just discharged it. We're going to put this onto diode continuity. Then we're going to buzz the board out and see where the power goes. Where does the power go? I'll move this down a bit so I can see. I think I might lower my seat. Yes. All right, this is a bit awkward for me because I'm right up close. All right, so this is the track. That track there is the pin 4 or pin 5. That's pin 4, and it's connected to there. So that 0 ohm is all right. Then it goes. Where does it go from there? Shit, does it go straight into a wire? What have I told you boys about putting B plus power into the wire? You ridiculous people, look. There's, can you see that track? There's pin number 5. Goes down to that track, to that via. So straight away they put the power through a piddly little via. Not a good idea. I've spoken about vias before. They're a disastrous idea as far as pretty much anything but signals, and especially high voltage track shouldn't go through vias, especially ones connected to capacitors with plenty of charge in them. Because those vias, you know, they are a very weak spot in the manufacturing process. So that via goes down to there, which is just west of there, isn't it? So that goes to there, that track there. So go back on there again. Yeah, vias are a bad idea. They are bane of my life. So that is the via there. That's the track. And we've got continuity. So transformer is connected. Then we've got, this is the other end of the primary winding, goes to this point here. So there's the primary winding. That should be, that's where the 200 volt, 300 volts should be. And presumably this winding down here must be the bootstrap supply to a diode and these that capacitor. Yeah, so there's the bootstrap winding. That's the low voltage winding to supply the unit when it's in operation. So we come through here to that diode on the top. Now that diode, I think, is the snubber for this power supply. Yeah, it is there. So that point there is the positive supply. Can you see that? I can get any closer for you or not. Now there's a track running down here. That's the B plus track. Going down to that corner, disappearing under there. I don't know if we can get a better look at that, can we? Pretty close and personal. Where are we? Focus, you focusing thing. There, you can get a good look at it now, can't you? Yes, you can. Look, somebody's been on there. That's been scratched, look. See that? Like someone's poked around with this, suddenly. A previous engineer has had a go, I reckon. And you can see it going down there, down there, down there. Down there, where it says C40, it disappears underneath that edge. When does it emerge from there? Right, so then it goes... Where are we? That's it there. Is that another scratch mark? No, that's a bit of glue. And then that's it, just... This is hopeless. If I hold it still, you can see the track there. And this is the top of that big capacitor. So, that track disappears down here, around there, around there, around this side, down that part to there, that one there, into that cap, and then presumably hooks up with the B plus on the second filtration capacitor. Now this might have been dropped or yanked or something, or the via might just... They feel quite tight, don't they? The via has failed, I think. Something's gone wrong. Something has gone wrong. Right, so I think the best thing to do is just whip those caps out, to be honest. Have a look, see what's under there, if anything. They look to both be glued together, so I'm going to take them out by heating them both up and just dropping them out the board. They're probably going to put up a bit of a fight. Come on, Mildred. What's the matter with you? Oh, I see. She's set to 300. Not for long. A bit of copper between them just to give it a bit of extra oomph. I'll reach around the back. See if I can get them out. Fingers are out underneath now. Come on. They're moving. Rock it back the other way. The thing about heating these things up is to be patient. Let it dwell. Then you can get them out. These two are stuck together, and then the glue that's on them is that white hard thermosetting stuff. It's really quite difficult to do anything with. There you go. So they're dropped out. Let's remove this. And whilst we've got her, where's my solder socket gone? There it is. Give it a quick clean with the mother sucker. Smoky. Open the window, eh? Right. Toothbrush. Right, so we've got two caps stuck together with that white cement stuff. What have we got on this? Ooh. Wow, look at that. Well, there's your problem, or one of them anyway. Let's just adjust the old iris. Can you see down in there? Got carbonised board. That one, the actual wire's just come off with the lead, and I gave that a good desoldering as well. It's probably stuck on the cable, is it? Yeah, it is. Stuck on the capacitor wire. What you had is a bad connection on this wire. The wires, as I said before, are plated through, so you expose and etch both sides of the boards, and you drill the holes through, but clearly there's no interconnection from one side of the board to the other, and the interconnection is done by a plating process where it goes in the bath and there's plating fluid driving through these holes, and the top and bottom tracks, top side and bottom side tracks, are connected by a plated connector through there. And as I said before, when we used to receive boards, we'd cut a piece of board out, encase it in epoxy, and then cut it, and then polish it, and then inspect the wires to make sure there's an adequate meet. And the trouble with wires, any kind of vibration of the components or anything happening, and this has been on a boat for 6 weeks probably, next to the engine room on a big shipping ship maybe, but the vibrations can cause these to crack, and moisture also, because there's often a residue of the etching process stuck in the holes if they haven't been washed properly. Wires are a real crucial part of the quality of PCBs. And in my experience, and I had 20 odd years of buying a lot of PCBs, is that some manufacturers were just bloody hopeless and never got it right, and others were very, very good. And the third category are the ones that had the occasional lapse, but were generally good, but had, got busy, had process issues, or bought in a bad batch of boards or something. But yeah, the wires, and also they haven't, you can see on this board, you can see the tops of these wires. Can you see that's just copper? That's just copper. If I show you over here, can you see these? These aren't plated through. Normally you would have a board, every board I ordered, I think, unless it was a specialist with very fine surface mount, which this does not have. You'd have a Hassel board, HASL, hot air solder leveled, where the board was fluxed and tinned, so all the exposed copper, all this, would be tinned, ready for soldering. So when you did solder it, you didn't have to wet the solder. It was already tinned, And you made the holes a little bit bigger because the leads would have to go through, but it made a much better soldering process. And the interesting thing on this as well is, and I don't understand why unless these are test points, but this is a big issue. You can see that the solder has filled these wires up, but not that one. But these are tented wires where this solder resist epoxy coating, this green stuff, is screen printed over the board, and wherever you can, especially in anything that's going to be, you know, exposed to any moisture, you should tent your wires. And these are untented wires, and some of the equipment, the audio equipment, are terrible because you just need a little slightest splash of liquid, literally a few drops, to get in there. You know, someone sloshes a drink over an expensive audio unit, and with untented wires, the liquid goes in the hole, and then there's some action and the thing just stops working because the wire's gone open circuit or a high impedance, whereas the tented ones are waterproof, as you can see. So why don't you tent your wires, you silly buggers? I don't know. So going back to this, I don't know if we can see this a bit better on here. You can. Look. You've got unsolder leveled boards, so there's not tinned. The solder has wicked up the hole to an extent, but on this one it hasn't. Look, there's no solder in there because it's probably the copper went dull, there wasn't enough flux put on. So the only connection on this board was to the other side, and clearly the wire was in the middle of the hole. So if the wire was open circuit, it would have been sparking between the wire on the capacitor and this, and it's basically carbonized this, caused this cancer on the board, and there's the end of the track that it's supposed to be connected to. So there she is. Okay, so there's your problem. Bad design, bad manufacturing, needless, pointless, stupid fault causing a problem. And the worst thing about this is, anyone's got any experience in designing power supplies boards, it's totally predictable. You never put your power through a wire, and if you do, you have an area of copper here, and then you stitch with several wires. So you've got 5 or 6 wires stitching the power, giving you that much more resilience to one failed wire. Okay, so I've cut that off there. Let's turn attention to these caps, see what we've got. Very small caps, 47 microfarad, 400 volt in a 12.6 case by look at 12.6 millimeter case by 30, and they are Samsung. Not a great reputation, these caps. If you look on the online forums, people don't like them. Someone clean underneath. It's clean enough, doesn't it? Ah, this one shit the bed, look. Look, that leg has been eaten through. That leg's really a stiffy. That one's not even connected to the capacitor. Yeah, it's been eroded, and then whether it was the arcing caused the leak or the leak caused the arcing, but that has failed. Can you see the corrosion there? Green spot. Wee green spot. So there's your problem. Now, I don't know if I've got any of these or not. These are an odd size. I noticed that Nippon Chemicon make what they call compact design, and it's really is a compact design. If I just get one from the box, hold on. There you go. Look, this one's a bit of a large one, but 47 400 volts. 47 400 volts. You can see the difference in volume. Of course, the difference is this one's reliable and this one isn't. But I think Nippon Chemicon have bought out a range of these which are very compact, and they call them the compact range. And I think Samsung and everyone else has been tempted to follow suit. But the thing that caught me on the Nippon Chemicon datasheet was that they were quoting 10,000 hours at 105 degrees, which is amazing for electrolytic capacitor, which really, you know, is normally they're 2,000 or 5,000 hours are expensive, but 10,000 hours at 105 and such a small package almost indicates a new technology. You know, they found a new way to get more capacitance, more reliability. And when Nippon Chemicon tell you that it is, I trust them. But when anybody else ever tells me it is, I don't trust them. I'm going to have a look. I think I bought some of these for a lighting design I did. Let me have a look. Yeah, as it happens, I do have some. These are from RS. These aren't the Nippon Chemicon ones, but the Nippon Chemicon ones are only available from Mouser, and they charge a huge shipping cost. But I have ordered some from LCSC. Now, you can see that, yeah, that's the part number, RS number 7683992. They're manufactured by Nick, old Nick, NIC. I'm just going to slice her open. Right, so they're stating, they look quite nice, don't they? But I don't know Nick as a make. Anyone? Anyone know? Japanese look. I think these are probably quite good. And I wonder if these are badged by Nippon Chemicon. Because it's a very rare format. But nice, eh? But these were like £2 each, I think. So there's 2 of those. I wonder if the other thing has got any power left in it, any capacitance left in it. Let's have a look. Yeah, let's have a look at this and see what we've got. So, predictably, on the watt capacitance, they actually say, because quite often Chinese capacitors, if it was a specification of minus 20%, and if you had an 100 microfarad capacitor, it would nearly always measure 80. The Chinese ones are always on the lower end. So we're testing at 120 hertz. See, we've got 40 microfarads, and it's supposed to be a 47. We're testing at 120 hertz, I think. Yes, we are. That's the correct frequency. Yeah, so we've got 40 microfarad, not 47 at this frequency. Right, so where's the other one that came out without the broken lead on it? There it is. So the question is, do we put this one back in, the Samsung, or do we not? What have we got on this one? Oh yeah, lovely, 36. Oh no, 40. What's going on there? Bad connection? 40.72. And 1.3 ohms ESR. .9. Let's get it stable first. Yeah, so it's much higher ESR, this one, but it is an aged capacitor. Do they look the same? No, they don't. You can see the seal around the bottom is completely different, so they're not from the same mill. So I'm going to treat this YouTuber and put 2 of those in. And, you know, when you're repairing switch mode power supplies, you should always think, okay, well, that component's blown up, but when that's been sparking and arcing across that connection or carbonising that board, you think of the grief that the actual semiconductors, namely the PWM management chips, have suffered. They may work now, but I'm not even going to bother powering them up. I'm just going to change the chips. So there's the 2 of them. So I put those in. And then the other chip is this one. NCP 1207ADR2G 7868806 from RS. We can have a look at the data sheet if you want to have a look. I think we have it here somewhere. There she blows. So it is a quasi-resonant power supply chip, and you can read that at your leisure. If we scoot down here, yeah, up here we've got the mains coming in, a reservoir capacitor, a resistor, or an external component with a star on it. Presumably that's to share some of the dissipation that's going to happen inside this startup circuit connected to pin 8. You've got the bootstrap supply here. Oh no, it's not bootstrap supply actually, but it's probably derived from pin 1. That's to do with the signal from the transformer to detect what the flux state in the transformer is, so that you can do the switching at the right time to make efficient switch over to improve efficiency, basically, and keep the FET cool. That's why it's called a cool FET, because the FET is only really switched during the troughs when the current is near zero. Secondary side, rectifier, capacitor, Zener, optocoupler, demand pin to pin 2, and then a current sensing pin here to pin 3, presumably. But the important thing is what's connected to pin 8. Let's have a look at that, see what the supply voltage looks like. So that was called, the pin 8 was called the high voltage pin. So what's connected to the high voltage pin? HV. Okay, so HV is down here. We've got a 7 milliamp pump circuit pumping enough current down in here to keep this VCC energized. Alright, so it is driven from this, but this is a switching circuit, I think, and it gives a 12 volt out, but that is going to be a sensitive circuit, so that won't have liked being messed about by the high voltage input wanging around. And then there's the rest of this, quite a lot of electronics inside here. And the final device is this one, what you can get from RS. That's the manufacturer's part code there. You saw it on the data sheet earlier. There it is. RS code number 2432501. So we need one of those. So let's just change those chips. What we're going to do is what are we going to do? These are the components we're going to put in. And we're going to take the chips out, and then we'll scoot around with a meter and just check the low voltage resistors to make sure that everything seems more or less okay. I can't see any scarred or blown resistors. Usually when the resistors go, you can see some kind of scarring evidence on the top surface of them, but there is none, so we should be all right, I think. All right, so what do we got? Chips. Let's take that one off first. Number 1, noting that pin 1 is closest to me, I'm just going to put a little of the bit of the old flux on there, because as everyone knows, things go better with flux. And now some nice relaxed soldering. Just going to use a soldering iron to save overheating the board, overstressing. Plenty of time. Stay calm. And the other side. Must open the window. A bit more on that side. Okay. So that's lovely. Beautiful blobby solder. Unleaded solder. Sorry, it's leaded solder. Much better for this kind of thing. For rework, use leaded. There you go. Bear in mind that this was stuck on with epoxy, so there's a little blob. If I turn her over, you can see it. Can you see that little blob down there? Right. So she can go in the junk box. It's a home for failed components. There it is. Just pick up that solder from there. Lovely. And helpfully they haven't actually put which way round the chip is intended to go on the board. There's no ident, which seems to be a bit of an oversight. Right. You can put the chips back on without sucking off the solder, but it's not a great idea. Right, we're going to give her a bit of a clean in a minute. I'll show an easy way to get these chips out. I wouldn't normally do it this way, but seeing as you are here and I'm here, and you may not have such a powerful soldering iron, you can get a pair of fine snips and just cut the legs. Careful not to pull on them. Careful not to disturb the board. These aren't the best cutters in the world. They've had quite a few hot dinners. Now you can see, look. Well, now what? Oh God, that's not very good, is it? I need more magnification. But you'll get the gist. I'll just do this. I'm going to put a bit of flux on there because I'm a sad old man with a flux fixation. Now if we just heat them up, we can just lift the pins out like that. Can you see that? Okay, no trauma, no fuss. And if you want to get the other one out, the other way to get the, if I just raise it up a little bit, what have we got in that box? What you can also do is this, to get your chip out, solder between the pins. Make sure you do this in a well ventilated area, obviously. You can solder between your pins like that. And then you can whip it out with this soldering iron. She's gone, boys. The chip has left the board. Now this one has got the orientation of the chip on it, which is nice. And then remove the excess on this side before we give her a good sucking on the other side. Turn her over and give her a good suck. What could possibly go wrong? There we are. Lovely. Nothing better than electronics in the morning, is there? I wonder how many CTEK batteries charges this will save from the skip. My ultimate goal would be to stop them replacing them without taking responsibility and repairing them. That resistor's just been dislodged. Yeah, everyone starts because also, you know, when you're an electronics manufacturer, you have to register as a waste disposer, right? And if people return things to you, you have to responsibly recycle and dispose of them. So really, by not taking it back, they are actually shirking their environmental responsibilities, A, by designing a product which just goes wrong, and B, by perfectly simple to repair product is thrown away, and a new one is generated using the take, make and throw away philosophy, costing the planet for bad design. I make a bad design, customer pays for it, and then ultimately the planet will suffer. Why not make it last 10 years at least? Mandatory quality, fitness for purpose and reliability. Mandatory. Never mind these stupid CE things that nobody complies with anyway, because all you need is a constructor's file and a lack of integrity, and then you can flout the regulations, never get found out, never get told off, and again cost the planet and the consumer dearly. Right. A bit of a scrub up. Bit like my wife, she scrubs up nicely. Alright, so you get the gist anyway. So we've got to pop the chip back in. Come on baby, you can do it. In she goes. I hope. Bend the legs slightly. The legs open too far. Oh, can hear someone at the door. More electronics arriving, probably. I think it's the man. We've got one of those smart meters bloody things, and they can't read it. So I was like, how are you going to actually accurately charge me for my electricity if you can't read the meter? It's gone wrong. So this is the man coming to fit a new smart meter. I better go and answer the door. I'll fix that resistor in a moment. No, that was posty. Loads of parcels for the kids, none for me. Trying to get a nut off my Jeep. It's a 1 3/8 AF nut on the crankshaft pulley. It is tight. It's been on there. It's a 1946 Jeep. 1945. So it's been in there best part of a fair old bit, and it doesn't want to come off. So we've tried several schemes to make her do the do, and now, yeah, postman's supposed to be bringing me a set of impact sockets, 3/4 inch drive impact sockets to use on a big nut buster gun that I've got. I didn't have one to fit, so that's the next thing, to try and get that off. So that's that chip in. We are done with that one. Nice new chip in the right way round. Double check. And clean all the crud underneath these high voltage chips before you put them on. Make sure there's nothing that's gonna cause an issue with leakage between the pins. Too much coffee this morning. You try drinking 2 strong coffees and then try doing this. You get the yips. On a tiny scale, the caffeine really affects your motor functions in terms of accurate registration. It's me yakking away and you can't even see what's going on, can you? Right. Pin 1 in the same orientation? Yes, it is. Alright, there you go. So that's her done. I'm wondering how the power gets over to this chip here, the MTP. Wonder where that track connects to it, because I couldn't see unless there was another track under that capacitor. Did you notice anything? Do you know, I can't see where that track, it goes up there to this part of the board, the B+, but where's the B+ that supplies this power supply come from? There is a track, look, coming up through the same method, all the way down there, all the way along there to the top, to this point here, to one of the linking capacitors. Which I'm kind of surprised to see that connected to the positive side of the supply. They can't have done that, can they? I'm wondering if we put these caps back in, whether they actually run in a balanced way. They have to, don't they? Because they're connected in parallel effectively by that coil, just a filter coil between the two of them. Curious now, because that's the B+ supply, look, and there's just that one track goes around the houses up to here, to there, into the primary. Where does this get hits? Oh, I know. There was on that transistor connection up here, wasn't it? On this one there was 300 volts. Oh, okay. I think. Yeah, there must be a track between here and here. Through a wire. Again, we love our wires. Right, okay, so that settled that one. So that did have 300 volts on the transistor, so we're okay. So what we've got to do now is to decide what we're going to do about this track here, this one, this buggered up track. I'm just going to pull the end off if I can. I'll have to cut it, I think. Right, so we cut the track off. We're going to give it the carbon canker scrape. There's no other tracks nearby it can spread to, I don't think, so we're okay. Just remove that bit there right next to the... It was working its way across. When you see one of these in action, it actually looks really pretty. There's little sparkles. It's like fireworks going off on a tiny scale. Once had a multi-layer bulb once. It was incredible. It was all lighting up inside, and it was, you can see all the patterns, and it was pretty. And I said to the owner, I said, "What did you spill in that equipment?" They said, "Oh, it was Ribena, which is like a blackcurrant cordial." So it was neat Ribena, the sort of syrupy stuff. Got the bottle fell over and glugged into it, and it did the most amazing amount of damage inside. It was incredible. Right, so what do we do with this track? I think we should just take it from up there. So it should go on the, essentially there, which is input to the transformer. We'll put a wire around that peg and then come down and put it around the positive lead of our capacitor here. So we'll put an external mod wire to replace that track. That's what we'll do. So as you know, capacitors, the long lead is always positive. That's how the girls know how to, or the boys know how to slot them in the board without looking, basically. So these are Jap capacitors going in to replace Chinese ones, so I think if you're a betting man you'd think it would stand a better chance of survival. Right, remember to leave that one a bit longer. Spread the legs. I hope you guys can take what I'm showing you and go off and find some more, because this one's failed that way. The chances are another one will too. Will have failed in the same, for the same reason. Of course, the important thing to do when you're doing repair is not to put your cutters down somewhere. Good job you can't see the rest of my bench. It's not that tidy. All right, and we'll solder it onto this one. Now, as to whether this is going to actually bloody work or not, who knows? What do you think? I can't see any other blown components, and I did have a quick poke around with the transistors. We checked the diodes. There wasn't any real reason for, there was no sort of catastrophic shorts on the board. There was no indication of overcurrent. But that doesn't mean to say it's going to work. Right, this is PTFE sleeving, so it's heat proof, not heat proof, but very, very heat resistant. Good wear, unlikely to wear through. And now we've got to connect it up to this point here where that 0 ohm resistor is. Do you remember? Take it along there, down along there to that point there. On the inside of those pins, like that, and cut it just there. It was the cathode of that diode. There. Crimp it on. cut it off. Look out where the tail of that went when I cut it off. Make sure it doesn't get stuck on anything. And then put some solder on it. Push it down. Okay. Remove the solder tail or the wire tail. Right, okay, so that's what she looks like. The question is, does the bloody thing work or not? What do you think? Give them a bit of a clean as well. Alright, that's how well these wires were soldered. Look, the mains wires have just dropped off. Can you see that? I'll just show you over here. See the end of that wire? It's pretty well corroded. Black, look. It's supposed to be copper and silver. No stress relief on the wires. I suppose they shouldn't be expected to be bent that much, but doesn't look very good, does it? It doesn't look great, in fact. Let me just skin those off and then we'll put those back on. Right, I'm going to stick 80 volts on, something like that. No, less than that, probably 50 volts, and just check that we've got some B+ coming through on these devices. I've resoldered the mains lead up this corner, tidy it up in a moment. Live and neutral is marked on the board, which is good. Good. So let's just set this up so you can see it. There we go. So we'll see if we've got any volts coming into this thing. We've got our caps in the right way, we've got our chips in the right way. Brown trousers on. Much else we can do at this point. No. 2 new caps, 2 new chips, a new piece of wire replacing a piece of missing track, which is connected to the primary of the transformer, through the primary down there to the switching pins on the chip, which is in the right way round. Can't put it off anymore, can we? So let's put power on and see what she does. Or doesn't. Oh, nothing spectacular, and yeah, lower current. Doesn't look right to me. Something's not making contact. Just to see what voltage we've got on our capacitor. So we're on volts on the meter. On volts on the meter. On volt. There we go. On volts on the meter. Got 67 volts. And I can hear it trying to start, actually. I can hear it going chung, chung, trying to start. That's good. Obviously, we've got voltage up here. So the real... Oh, look. It's me talking away, look. Me talking away. And look what's happening over here. Can you even see that? Why can't you even see that? Oh, you can. We have life. We have life. So let's turn the power off before she gets totally confused. Yeah, so I think it's fixed, don't you? I think we've got life. She's showing signs of life. So you want a free battery charger from CTEK. Just tell them yours has failed, cut the wires off so that you can join them back on, and they'll send you a new one. We'll put pay to their dastardly plans, won't we? Right, okay, so now what we're going to do is run it up and see if the LEDs come on, and then that's a fix, isn't it? So I'm just going to take that off there for the time being. There we are. Right, here we go. Here we go. Brown trousers on. 200 of our mansions volts going in now. Yep. Don't know if you can see that. battery's not connected, so we've got the warning lights coming on. Yeah, so that's fixed. I'll put it back in the case and test it, and if there's anything else worthy of note, but I think the power supply side is done. That is a fix. So I hope you enjoy watching that. If you can, subscribe down there. I know it's going to be boring with all these battery chargers, but I'm a sucker for a sob story. Bought my battery charger. You know, a lot of people, not saying this guy's poor, or I'm not poor either, but you know, a lot of people, it is quite a lot of money for them, and it's nice to do something which will stop stuff going in the landfill. So leave me a like. Thank you very much, and I'm signing off.